In this video, we are going to go over oxidation reduction reactions, the oxidation reduction of hydrocarbons, and catalytic hydrogenation. So oxidation reduction reactions, these are energy transfer reactions. They are the transfer of electrons from one reactant to another reactant. One reactant loses electrons, and this is a process called oxidation. And the electrons lost are gained by the other reactant, and that is known as reduction. So oxidation is loss of electrons and reduction is gain of electrons. One mnemonic that is used to remember this is oil rig, where oxidation is loss and reduction is gain. So oxidation is loss of electrons, reduction is gain of electrons. Recognizing oxidation or reduction of an organic substrate is one way is by noting the change in the number of hydrogen and or the number of oxygen atoms. So instead of looking at finding oxidation states, things like that, for organic reactions or organic substrates, looking at the change in oxygen or hydrogens bonded in the molecule will help you easily recognize if something's undergone an oxidation or reduction. So if there is an increase in oxygen atoms or a decrease in hydrogen atoms from the substrate or the reactant to the product, then the reactant underwent an oxidation reaction. It lost electrons. Reduction is a gain, remember, it's a gain of electrons. And if the reactant either lost an oxygen or gained hydrogen atoms, then it was reduced. So oxidizing agents. An oxidizing agent is a reactant that is reduced and causes the organic compound to undergo oxidation. So a substance that is reduced in a reaction is called the oxidizing agent because it helps the other product or the other reactant become oxidized because because of that transfer of electron. This O right here, when you see this above an arrow, this symbolizes oxidation. So you can see that it changed from an alcohol to an aldehyde. And then in liver cells, the oxidizing agent is called NAD+, which is reduced to NADH. And we gained a hydrogen, and this is a reduction. So reducing agents are the opposite. So the reductant that is oxidized causes the organic compound the other organic compound to undergo reduction. So this, when you see this H here, this is a symbol for reduction. Commonly, this is NADH, which is then oxidized to NAD+. H2, so hydrogen gas, is also a common reducing agent, especially in the lab. So these are common oxidizing and reducing agents. Oxidizing agents, we have bleach, oxygen, hydrogen peroxide, chromium 6, I'm sorry, NAD plus and FAD, and those are coenzymes. And then reducing agents, hydrogen gas and sodium borohydride, those are commonly used in the lab. And then NADH and FADH2 coenzymes, and then vitamin C as well. So the oxidation reduction of hydrocarbons. So an alkyne can be reduced to an alkene. An alkene can be reduced to an alkyne. The number of hydrogen increases by 2 with each reduction. Remember, if you increase hydrogen, it is reduction. And this is because if you increase the number of hydrogen, You increase the number of electrons because you're adding bonds. And with oil rig, you have reduction is gain of electrons. The reverse reactions, or oxidation, requires a carbonyl or an aromatic ring to be present next to the carbon atoms undergoing an oxidation, since carbon single bonds, so carbon-carbon single bonds, are unreactive. We can see here on this chart on the right-hand side, oxidation, we have an alkane, goes to an alkene, goes to an alkyne, but it requires a carbonyl or aromatic ring to be present next to that carbon. The other direction, reduction, goes from alkyne to an alkane or alkene to an alkane. So catalytic hydrogenation is a type of oxidation reduction reaction, and it is the specific reaction of the reduction of an alkane to an alkene, or an alkene to an alkane. So a double bond, carbon-carbon double bond to a carbon-carbon single bond. This is performed in the lab using hydrogen gas as the reducing agent in the presence of a metal catalyst. So you need hydrogen gas and a metal catalyst. The metal catalyst is usually palladium, nickel, or platinum. It is used commercially to prepare partially hydrogenated fats. So the hydrogenation of unsaturated fats reduces some of the carbon-carbon double bonds in the unsaturated fat, forming a fat with a longer shelf life and a more solid, spreadable consistency. So during catalytic hydrogenation process, some of the double bonds are not reduced, but instead isomerize from cis to trans. So not everything doesn't go all the way to completion. Sometimes those double bonds don't go all the way to single bonds. They instead go from the cis double bond to a trans. Fats containing cis bonds are healthier than fats containing trans bonds. If you ever heard of cis fats or trans fats are more unhealthy than saturated fats. So we have a cis alkene right here, and you add hydrogen gas with a metal catalyst, and you can get the single bond. The carbon double bond goes to a single bond, and you can also get the trans product. So when you have the R groups or the H groups on opposite sides of the double bond. Cis is when the R groups or the H groups are on the same side. So what happens is when you have complete chemical hydrogenation, you form a saturated fatty acid. Remember, alkanes are saturated hydrocarbons, so it's all carbon-carbon single bonds, but you get the side reaction known as partial chemical hydrogenation, and you get the trans fatty acid. Remember, trans fatty acids are more unhealthy than saturated fats. So to practice, we're going to write the Lewis structure of the product formed in the following reactions. Let's go ahead and pause the video, and when you're ready, we'll come back and we'll work on them together. Okay, so this first one is a catalytic hydrogenation, and we have our hydrogen gas in our metal catalyst. This is an alkene to an alkane, so it's going to convert this double bond to a single bond, and this structure has 1, 2, 3, 4, 5, 6, 7 carbons. So I'm going to write out my carbons. 1, 2, 3, 4, 5, 6, 7. They all have single bonds now, and they all have saturated with their hydrogens. Because to create this single bond, we add hydrogen to each of these carbons and take out this double bond to create the single bond. We have the same same substrate or reductants here, and it says hint the carboxylic acid functional group is unchanged in this reaction. So this part, the COOH, is not going to change. The only part that's going to change are the double bonds. We have 2 double bonds in this molecule. During this catalytic hydrogenation, every double bond is going to be changed. So I'm going to count my carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 carbons. So it's all going to go to saturation. If this went to saturation, it could go to the trans. Remember, sometimes you have that byproduct of the trans fat. But if this was performed how you wanted it to be, it would be the whole saturated fat right there. So in summary, the oxidation of an organic compound appears as a decrease in hydrogen atoms or an increase in oxygen atom at the functional group. So this is important, at the functional group. So remember, organic reactions occur at the functional group. The opposite is observed for a reduction. In the presence of an oxidizing agent, the substrate is oxidized, the oxidizing agent is reduced. In the presence of a reducing agent, the substrate is reduced and the reducing agent is oxidized. A carbon triple bond can be reduced to a carbon double bond, an increase in hydrogens. A carbon double bond can be reduced to a carbon single bond, and the analogous reverse reactions are called oxidations. A catalytic hydrogenation is a common reaction performed in the laboratory to reduce an alkene or carbon double bond into an alkane, carbon single bond, using hydrogen gas and a metal catalyst, and hydrogen gas is the reducing agent.